All right, so in the next 40 minutes, I will be talking about random walks and local cuts in graphs. Because when we have big data, like 100 neurons or 200 million users or those things, our graph is so big that we are only interested to see just a subset of these vertices. And from this subset, we want to find some, we want to talk about conductance, Chiger inequality. And so everything is now local. We want to extend all of the theory of spectral graph theory to local things. To see what happens, for example, to conductance, what happens to those theorems. And Fan Chung has written a good book about spectral graph theory, and she's a good example of a person who has generalized all of these classical things to local things. So the Chiger constant, h of g, as you know, is the minimum of, if you count all of the edges that cross some subset, for some subset like x, which is a subset of g, then this is the classical definition of Chiger constant. And you know that globally we can say good things about eigenvalue, that it is upper bounded and lower bounded between h of g, the Chiger constant squared, and 2 times h of g. And lambda is just the second eigenvalue. You know, the first eigenvalue of Laplacian is 0. And just because of the definition of that. And so this is just the second eigenvalue. And locally, we can say good things about that. That locally, we can say that lambda is now h of s. S is a subset of vertices. As I said, in the world of big data, for example, Microsoft should use these local things because in order to do some parallel algorithm, in order to handle big data, they have to work on these local theorems. And everything again goes back to the Dirichlet boundary conditions. For example, in this equation, you know, in your interior, this is your interior. You have some, for example, on the boundary, u on the boundary is 0. So you want to solve this equation, and so this is it has discrete and continuous version, and in general, lambda 1 is the infimum of integral of this squared over u squared. You know, u is just a function that you want to solve. And luckily, it is very popular that lambda is just the infimum. This is the solution, but we want to do it in a discretized way. So we just rewrite it as f of x minus f of y. So, for example, in continuous Markov process, we go to discrete Markov process. And so we can always go to discrete and come back to continuous time because sometimes in the continuous time life is easier, and sometimes in the discrete time life is more meaningful. And so instead of just a very big matrices such as Laplacian, which is just v by v, we want to work with Laplacians that are a little bit smaller, like S by S. And so this matrix is much smaller than this matrix, and it's easier to deal with. And so another things that I wanted to mention is the work of Lowas and Simonovitz in 1990, and then they improved it in 1993. Of course, their problem was just looking for some volumes of a convex body, but they can use it for classical spectral graph theory as well. So the vertex boundary, which is delta of S, is just the set of vertices that U is adjacent to V. But the edge boundary that I set is just a set of edges that U is in some set and V is not in that set. And the local Cheeger ratio is just all the vertices that goes out, but now T is just a subset. Everything is the same thing and is just a subset. So the local Cheeger constant, as you might expect, is just the minimum of h of t for any subset of S. So what we are going to do is just talking about this eigenvalue and see what is. First of all, we order the vertices. For example, if f is a function from V to R, from vertices to R, such as, for example, the eigenvector of your Laplacian, so we just order that like this. This is a good technique that we see in many theorems. And just the Cheeger ratio with respect to f is just the minimum of h of v of fi. And now the Dirichlet eigenvalue, as I said, is just the infimum of r of f. I mean the Rayleigh quotient that I have talked in the first or second lecture. As you remember, is just the f of x minus f of y squared over f of x squared d of x for any x in S. And here x and y are adjacent. And if you work on this, you can write it as infimum of f, and by definition you can write the Laplacian ds minus as f. You can write you can write it as a Laplacian. I mean, you can write it as just a function, but now in a we call it Dirichlet space. It's just a function space, g and Laplacian over acting on g, and then divided by g and g. And now this is the big matrix, big Laplacian matrix. But the trick is that now this is the infimum of g and Laplacian, but in a subset S of the big data, which is all the vertices. And so S is just a subset over G and G. So what I want to say is that Laplacian of S, so we have a big world, big data, which is G. So we just say we are only interested in a subset of that, which is S. And then from this subset, we are looking for combinatorics of different sets, such as T, and the edges that goes out of this. So the Laplacian restricted to the S is just d minus half, and then d minus adjacency d minus half. So this is very easier because it is S by S, while the original Laplacian is V by V. So for practical algorithm in Microsoft, in Google, those neuroscientists who are working with 100 billion neurons in your mind, in your brain, then it's more practical. So I just want to talk about the classical things that we have done for Chiger inequality, but now we want to prove it for local thing. What happens to local? So the proofs of all of those inequalities are the same. We just restrict it to the local stuff. So we want to prove that h of s is greater than lambda of restricted to s, and h of f squared, h of s squared. And so the proof is very simple. Again, you write Ls as the Rayleigh quotient of f. So you write it as I said, f of u minus f of v minus f of u squared over f of v squared dv. dv is just the degree of v, as you know, v over s. And if you just expand it, if you just expand this, you will notice that it is just f of v minus f of u squared. But this time we want to write it. We want to just multiply this by 1. Now 1 is just f of v plus f of u squared. F of v plus f of u squared. So because this is 1, we can multiply by that. And if you do so, you will notice that this becomes this becomes greater than f of v squared minus f of u squared over 2 f of v squared dv squared. So we can simplify this by saying that f2 of vi minus f2 of vi plus 1. So this is the art of ordering. So order makes these terms smaller because we have ordered that. So when you multiply by the boundary of that set, number of edges that crossing that, and as you remember, this is just the some vertices, for example, v1, vi, this set, such that it is ordered. I mean, f of v1 is greater than f of v2 greater than. So because it is ordered, so this term, because these terms are only 1 when they cross the boundary. And then you can and then divide it by just the same things as before, f2 of v d of v squared. And now we can use just the definition of that Chiger. So this is just greater than f2 of vi minus f2 of vi plus 1 times h of f, which is the minimum of h of v of f, times degree of j squared, over 2 times f2 of v d of v squared. And because this is greater than h of, by definition, it's just greater than this, because h of f is the minimum of all of these things. And then again, this is greater than h of s over 2. So the proof is almost the same. We have just restricted to s. We have just used it for the local version. And this ordering is very, very important in algorithm. For example, Lowas-Simonovitz has used these kinds of orderings. Even the Cheeger sweep is like that. So we have used it several times. So you know that Cheeger, you know that Lowas and Simonovitz did a very great work on. They created an interesting theorem that I will prove. And many people like Lapchi Lau, they just understood it, and they made it more popular. But so we have many different proofs of Lowas and Simonovitz. The first one is of course Simonovitz and Lowas, but many people also try to prove it, like Lapchi Lau. And one of the greatest proofs of this theorem is the work of Fan Chung in 2007, and it is published in Linear Algebra and is in its applications. And you can see how beautiful, and the proof, and learning the proof of that makes us understand the main ideas in random walk as well. So I just state the theorem and then prove it. So the theorem is that if you have some lazy walk after t steps, you will have p of lazy to the t of v and u minus, so the distance to the stationarity is just bounded by something, and it is very attractive because you're bounding by something which is local in nature, and degree of v divided by degree of u, and beta t and v is infimum of all of the edges that is crossing this set. Of course, this is the global version, and then I will show the local version. J and t prime and v divided by minimum of volume of S, J and t prime and v, and volume of complement. So, for example, S F3 and t prime and v is just we have 3 vertices: U1, U2, U3. So the edges that is going out you can count. And then for S4 and t prime and v, it means that we have now 4 vertices: U1, U2, U3, U4. And then you count the number of edges that is going out, crossing the boundary. And then Sj, t prime and v, we have Uj, Ui, U2 up to Uj vertices. So you got the idea. It's a very combinatorial approach. Instead of just linear algebra, it's a little bit more interesting in combinatorics. And you can use